Hi there, my name is Hannah Bruns, and I will be presenting my thesis research for my capstone for my computer science major. Okay, so my thesis research explores the application of a modern randomized technique for computing the SVD with deterministic approximation problems. Okay, so just a brief introduction. Matrix decompositions have widespread application in scientific computing and numerical analysis. The singular value decomposition, or the SVD, is particularly interesting due to its applicability in solving rake-deficient and ill-conditioned linear systems and in solving linear least squares problems. Traditional algorithms for computing the SVD are computationally expensive, sometimes prohibiting their use in numerical approximation. We have applied a modern randomized technique for computing the SVD to deterministic approximation problems. Our target approximation problems involve linear approximation with approximants comprising radial basis functions, RBFs, and polynomials. We chose these as the matrices arising from these as the matrices arising from these approximates can be rank deficient or ill-conditioned. Our goal was to explore the interaction of the parameters from both the approximants and the randomized SVD algorithm. So, why use randomized matrix decomposition? It's a great question, but the biggest reason is because classic SVD computations are expensive as they focus on highly accurate decompositions. However, using a method or like this randomized method with the ability to control how precise you want the output is really powerful. You can kind of have a balance of accuracy to efficiency and find the perfect one for whatever you need. So this randomized algorithm I keep referring to, I'll now call the Martinson algorithm from here on out. We implemented this algorithm from the paper Finding Structure with Randomness, Probabilistic Algorithms for Constructing Approximate Matrix Decompositions. There are three parameters to this algorithm. The matrix to be decomposed, A, the tolerance or accuracy threshold, and the R value. This algorithm guarantees a certain threshold of accuracy based on the inputted tolerance. And the integer R is necessary to balance the computational cost as well as the reliability of the algorithm. So to briefly explain how this algorithm works is it draws a random set of R Gaussian vectors to interact with the original matrix A. As this happened, we examine the subspace formed from these interactions with random vectors. We do this for each iteration of the loop until it reaches the threshold for accuracy upon which the loop breaks. The output is an orthonormal Q matrix, which can be used to compute the SVD in a deterministic fashion. Since Q is much smaller than the original matrix A, computing the SVD will be much more efficient. And just to give a brief overview of the SVD, it is a matrix decomposition that exposes many of the useful and interesting properties of the original matrix. Also, it works well for solving rake-deficient, ill-conditioned linear systems and linear least squares problems. Okay, so with that said, going into our first method of approximation, in which we applied this randomized algorithm, which is a polynomial approximation. As a summary of what it does, it is basically fitting data to a model. So, given some set of points, we are trying to find a function that best fits these points. This creates the linear system right here down in the lower right corner, where these A's are the unknown coefficients. To solve this system, we are solving for these A values. And we are going to use the SVD to do this. So, to simplify things, this is what this can be written as. And instead of using the classic method to find the SVD of A, we'll now be using the Martinson algorithm. So our initial test on this algorithm showed substantial speedups from MATLAB's SVD computation. especially with a low threshold. So you can see in the top right-hand corner, when there's a more loose threshold, performs much better, and even better than the threshold in the left side, upper left, whereas both of them become more efficient than MATLAB's traditional SVD computation. So we'll move on to our first round of tests, which are using polynomial approximation in 2D. We're approximating the range function using point sets created from the Halton sequences, which are quasi-random nodes between 0 and 1 inclusive. We first tested the parameter tolerance. As you can see here, the tolerance or accuracy threshold has little effect on the relative error, which is encouraging since the speedups we saw previously were more substantial with a lower threshold. Moving on to the R value parameter, again, it appears to have no effect on the polynomial approximation in 2D, and the relative error doesn't seem to change based on the R value. Next, we move into polynomial approximation in 3D. We approximated the same range function using the same Halton sequence to create point sets. And again, we first started with the tolerance. Similar to in the 2D case, the tolerance appears to have little effect on the relative error with polynomial approximation. But as we move on to the R value, it appears that it has a little bit more of an influence on the relative error here. So it looks like when using polynomial approximation in the Martinson algorithm, you should keep the R value below 9. So after we did our initial polynomial approximation testing, we moved on to RBF approximation. And so first I'm just going to explain a little bit about what RBF approximation is. So RBS, just like polynomial approximation, I'm referring to it as RBS, but the extension is radial basis functions, and I'll be using RBFs. RBFs fit data to a model, just like we did in polynomial approximation, but using a distance matrix this time. So given some set of points here, we construct an RBF interpolation where CK are now the unknowns. Phi here is the polyharmonic radial basis function, and they're both being applied to the distance matrix. So from that, this system is formed. However, this system is notorious for being ill-conditioned, but one way that has been found to make it more stable is to augment polynomials, which is exactly what we do. So here we modify the RBF interpolation to include polynomials, which creates the following system here. In this case, psi is the van der Waals matrix. So you can say that would be here, and the van der Waals matrix is from the polynomial approximation that we were doing before, and A is the RBF interpolation matrix, and then we can simplify it down here in the lower right-hand corner as such. So to solve this system, we use the Schur complement. As you can see here, and so first we solve for beta, and then after we solve for C. And as you can see here, C and beta are just like before what we are trying to solve. So, and just as a side note, we use the LU decomposition of A to find the inverse of A more efficiently. So now that we know how this happens, now we'll go into the test. So we approximated the same range function using the same domain, the Halton sequences, using the same domain as well as the same way to create the point sets, which is the Halton sequences, and then first again tested the tolerances. So this is a little different. We ran these tests using two different polyharmonic or radial basis functions, where M equals L, and L in this case is the polynomial degree. So M equals L minus 1 when L is even, and M equals L when L is odd. So that's that first case here in the top, and then the second is when M equals 2 to the L plus 1. And this, it's a function of s, so we're just changing the exponent in this function. So as you can see in this first case, or this top case, a lower relative error was achieved at a much faster rate. Additionally, we can see that it spikes a lot later than in this lower case. So it spikes at a larger matrix, as opposed to down here when it's just at 20. However, in both of these cases, the tolerance doesn't have much of an effect, or it appears to have not much of an effect, just like how it was in the polynomial approximations. And the difference between these two graphs is the polyharmonic radial basis function. Next, we ran the same test, but this time using the R-value parameter. We have basically the same performance here as with the tolerances above, or in the last slide, but so we're this top graph, or with this value of phi, performing a lot better, reaching a lower relative error and at a faster rate. But as far as it goes, it seems there's not much of a difference between the R values here, and so it's not making much of an influence. So next we moved into the 3D case for these tests. Again, we use the same range function and the same Halton sequences to create our point sets. So we first tested the tolerances again. We use the same radial basis functions phi, and we can see here again that the top one has a faster rate of relative error decay and also achieves a lower relative error. And this one even achieves a lower error than in the 2D case with RBFs, but it's to be noted that like both of these RBF methods have achieved lower relative errors than in the polynomial approximation case. Again, we notice that same spike. This one is a little bit later with the larger matrix, while this one is earlier, the bottom right one. And so then we'll move on to the R values. Again, these graphs look almost identical to the ones above when testing tolerance. Both of these parameters, tolerance and R values, don't seem to make much of a difference in the 3D case with RBF augmented with polynomial approximation. But it is important to note that the polyharmonic R radial basis function phi makes a significant difference in both 2D and 3D cases of RBF interpolation with augmented polynomials. So to summarize, in both the case of 2D and 3D, RBF interpolation with polynomials achieved a lower relative error and at a faster rate. But it's important to note that, again, these was on the specific value of phi, whereas when phi equals s to the m, where m equals 2l plus 1, did not perform as well as the first. But both of these RBF approximation methods outperformed the polynomial approximation methods. In conclusion, I think we learned a lot from these experiments, the most important being that a loose tolerance has little effect on the relative error, which is great news as the Martinson algorithm is more efficient with a looser tolerance. Additionally, it appears that the algorithms produce better results using RBFs augmented with polynomials as opposed to just polynomial approximation. I think we learned a lot from these tests, from these experiments, but there's still a lot more to learn, so we plan to do future research in higher dimensions with data lying on lower dimensional manifolds where polynomial matrices become more rank deficient. And that's about all I have. Thanks.